Here's your next assignment. Just posted to the Blackboard about half an hour ago. Excuse me. I'm 95% sure I'm not sneezing COVID. Because I've been vaccinated, so. Let's see, so this is due Monday, a week from this coming Monday. And what we're going to do is model the robot arm, the rotary robot arm with a neural net. So the model, the architecture I've shown you there is exactly what I want you to use. You're going to predict theta and omega at the next time step, and x1 and x2 at the next time step based on the current theta and omega in the current torque. So what goes in the middle, I've defined the inputs and the outputs, so you decide what else goes in there, how many bit nodes, how many neurons. We don't have a robot to measure the values of x1, x2, theta, and omega. So we're going to use the math equations as if it's a virtual robot. So we're modeling the differential equations just like we talked about last time using a neural net. Our training data is going to come from the differential equations. So what I've done here is integrate this differential equation to get omega. That's T over J times T. And by the way, T is a constant in what we're doing here. So it makes the integration easy. You don't have to solve it for an arbitrary torque time history. And then you integrate that one more time, and you get T over 2J T squared. And because I chose initial conditions of 0, there is no extra constant there. So really, we're starting the arm out over here at rest. And we kick on a constant torque, and it starts to rotate like this. So in a spreadsheet or in MATLAB, you will simply use these equations, and you're going to do this for time steps of 0, or time values of 0, 1.2, all the way up to 1.1. So anyway, that's going to be 11, right? Now we're including 0. Yeah, I should, there are 11 training pairs. And we're going to do this for 4 different torques. T equal 1, T equal 2, T equal 3, T equal 4. And those will be your training set. So you have a spreadsheet where you put T equal 1 up into the equations there and do T equals 0, 0.1, 0.2, 0.3 to generate the data for that. Then you do the next torque and the next torque and the next torque. And calculate all the thetas and omegas and the x1s and x2s. And remember, x1 is just L cosine theta, and x2 is L sine theta. We did that last time. It's just the trig. So I'm giving you the arm length J. Also, the moment of inertia J, the arm length is 2.5. We're doing the time step 0.1. So you will end up with 44 training pairs in your training set. And then you're going to create a testing data set, and that's going to be from those torques there in between and outside the range that we've already done. And we'll see how well it works. So your main job, actually the hardest part of this is not so much running NeuralWorks, it's just getting the spreadsheet or the code set up to generate your data. And for this problem, it's not that hard. You're just, I mean, you can see how to do it right away, right? So you're going to write up your results. Make sure you show me more than just your final network that you end up with. Show me things you tried. Right, you're going to try different architectures. So make sure you show me that. Give me exactly a 1/2 page description. Don't make it a page. Don't make it a page and a half. Don't make it a quarter of a page. I want to see a 1/2 page. Make sure you tell me how many neurons you use, what are your activation functions. You know, essentially, tell me everything I would need to know to recreate your network in NeuralWorks. And the number of training pairs processed is like that 50,000 or 60,000 or whatever you tell it when you do the run and learn. Show me a printout of your network screen. Plot the training data and plot the testing data points. And then show the actual testing data points and the targets. So show the targets and the actual values. And notice it says do not connect with lines, because if you connect it with lines, the lines cover up the data points because it's going to be in a circle no matter what. And don't auto scale your plots, because it might do, some of them will just be within a small region over here. And if you auto scale, then everyone looks different. And I want to see it scale -3 to +3 so that it looks like a circle as it goes around. So you're going to submit the document with your write-up and your printouts. When it says a printout, you print it out and then you scan it in and upload it to Blackboard. But I also want you to upload a zipped folder named with the first letters of your last name. Do we have anybody that has the same last name in here? I don't think we do. I don't think so. Make sure you name it that way and zip up those files that I'm asking for, which are what? The NND file, that's your network file. You save the network. And then your testing and training data sets. So your TRA.ANA and your test.ANA. So that's the 2 data sets up there. Make sure you give me this file. Often I'll have a couple people that'll forget to give me their network file or give me something like the NNR file. But I want the network file so I can load it up and run it. And please just use normal zip. Don't do 7-zip, G-zip, RAR, stuff it, or a whole bunch of other stuff. 7-Up, Coke, or Pepsi, those are a joke. But there's all kinds of compression algorithms, and I don't have them all on my computer. So just keep it simple. Questions? It's due Monday. Don't wait till Sunday night to start this, because if you run into problems, I won't be able to help you. So start early, give it a shot. It's not that hard of an assignment. It's kind of fun. You get to generate data and you go over and play around with neural works and optimize. Hints on network. You want small error, as small error as you can get in the training and testing. But don't go crazy with the number of hidden neurons. Smaller network is better. Now, too small is not better, because if you don't put enough neurons in, you saw that with the iris, right? You don't put enough neurons in, you don't get good results. But it tends to, if you make the network too big, it tends to not test well. It learns the data over here really well, but it doesn't test well. It's kind of like overfitting a set of data points with a polynomial. If there's some noise in the data, if you fit it with a high order polynomial, you get this weird gyration thing. Questions on the Zoom channel? I don't see anything. All right, we did that. I want to show you some architectures that we use for controls. Let me do that. Actually, let me hand you that. This is the assignment we did last time. Ali, Graham, you and Graham. Lynch, EJ, Caitlin, Daisy. Daisy, right?
Yeah.
Anna Forrester. Really, I'm going to think after a couple of semesters, I don't know. Collier, Aaron. Yes. Ryan Eason. H. Carmichael. If you scanned it and uploaded it, if you weren't here and you did that, it'd be great. If I just don't have a film of it. Right, so these are different control architectures. In other words, just different ways that you can use a neural net to control the system. And what I'm going to draw up here are kind of high-level pictures. I'm not intending to show all the inputs to the neural net or how many hidden neurons or anything like that. It's just more like a block diagram. So we'll look at what's called the tracking problem. We'll do other problems, but this is a good way to illustrate the way this works. So we have an actual physical system. And it has an input U. It may be a vector of inputs. And then it has a vector outputs. I'm not going to put the vector symbols on there. And we want to put a controller in here that figures out what inputs need to go into this to make the output match some reference or tracked input. I mean, something simple is we want the output to be a 5, let's say, and so this figures out that it has to input a U of 12.3 in order to get a 5 out. So we could replace the controller with a neural net because the controller can take a number like 5 as an input and learn to output the correct response U that gets the system to do what we want. So here's my general generic neural net picture. Like that. And so let's say we put in an XREF value, let's say we put in the 5. And the neural net doesn't know completely how to do this yet. It hasn't learned everything. And so it puts out a U of like 9 instead of 12.5. So if you put in the wrong input into the system, you're probably not going to get the correct output here that you want to match the XREF. So you apply an input. XREF. You observe the response of the network U, and then you also stick that into this physical system. You get the output. And then we look at compare the two, and we can calculate an output error or a tracking error. Reference minus what we actually got. And so we look at that and we go, okay, now we have an error here. But to train the neural net, what we really want is an error here. We want to know, well, how was U wrong? So then we can tell the network next time it ought to give you a 12.5 instead of the 9. So that's very similar to the problem we had with hidden layer neural nets. is that we had errors at the output layer, but we didn't know how to get the errors back to the intermediate layers. This is not a neural net right here yet. This is just a physical system. So the issue is, well, how do we get that error back here to figure out, well, how do we change our network? So there are ways to do that, and I'll show you that. But first, let's start out even simpler than that. So the first architecture, the first method, is a method that I do not recommend you use in any of your classes at Wichita State. And the reason for that is this is copy an existing controller. Which would work if as long as you pick the right controller, right? You're in a class, you're taking an exam, the guy next to you knows how to control his answers to get the good grade, right? So you copy his strategy. Hopefully you don't. But that's one way you could get the right answers, right? So if we have an existing controller that works, we could copy with a neural net just by saying, well, here's our existing controller. We put in a bunch of XREFs to record the views, and that's our training set for the controller down here. To get the physical system, we just use our existing controller, whatever it is, an algorithm or mechanics or whatever, and put in a bunch of inputs, collect the outputs, and then that becomes our data set. Because that's exactly what we need. Collect a bunch of data, and then you train the neural net controller. The obvious question then is, well, why? Because you already have a controller that works. Why copy it with a neural net? One case may be that the controller is a computer algorithm, but it takes a long time to calculate the control. So it can't run in real time with the actual system. So maybe you have a really complex control algorithm. And so you just copy the results of that. You don't have to do it in real time. But then the neural net is simple enough. It can run fast and it can do real-time calculations. So that's one reason. The other reason is maybe the controller is a human. And so you copy the human. We'll look at a couple different examples of that. One is pilots landing an aircraft. So there you can collect data of the best pilots and their best landings and what they did to nail the landing. Use that data to train a neural net to replicate what the pilot does with that aircraft. Same thing for a distillation column. We'll do a control of the distillation column. And humans know how to run these things. They've learned over a long time. We can essentially mine their expertise and copy it into a neural net. Kind of like some of those stock trading apps did. They picked somebody in the past that did a really good job of picking stocks and then trained the neural net to do the same thing. Okay, so that's architecture number one. And it works well. You have to have the controller ahead of time. And you have to put in enough different inputs here to generate outputs here to get the data set that covers the whole range that you want to operate on. But as long as you know that and you can generate the data, you can do this. So examples are like the distillation column, pilot flying an aircraft, other things like that. Okay, method two. plant inverse. Probably the best way to illustrate this is to just talk through an example. Over here. And we don't need this anymore. So forget the neural net for a minute. And let's say that for u here, we just say, oh, let's put in a u of 5. 0.5. And I run the plant, go through the physical system, or whatever it is, airplane, distillation column, and I get a 10 out over here. So far, so good? That's my input, there's my output. So now my question to you is, if I want to get a 10, what u do I use? 5.5, right? So that gives me a training pair. I put in a bunch of different values here, I see what I get out, flip it around, and then I say, well, I put in that value, and so I should get a 5.5 if I want to get a 10 out the other side. So it's the flipping around, you're essentially inverting the physical system. The controller is the inverse of that. And so one way to draw that is to draw the physical system like this. You're putting u values in, you're getting x out values out. And then you take your neural net and you drop it backward. Because we're going to put what we got out in, and then the target is going to be what went into the system. And so you collect data and run the system. Collect data. You send in u values and you get out values, and then you invert. Literally, you just flip the columns. Put in x out as your reference that you want, and then the u that you collected is going to be the value that you trained to. So there's some issues that we have to deal with. One is you must input enough u values to cover the range of x ref values that you want. And that, in simple problems, it's not hard, but in general, that may be difficult. Because you say, okay, I want to operate this system over a range from 0 to 100. What values do I put in here to get that 0 to 100 output? I may not know. And that's a single variable system. If you have a system that has 10 inputs and 4 outputs, then how do you figure out what values you put into all of those different ones to get the range of the output values that you want? So you got to be able to do that, and the system must have an inverse. Or in mathematical terms, the inverse that must exist. And so here's a real quick example of why that's an issue. So let's say we have the system and we put in a 5 and we get 22 out. And then we take the same system and go, okay, well, we're going to change u, so let's go to 10. I put that in, I get 22 out. Then I go, well, let's put it in 15. I get 22 out. And you think, well, gee, all I ever get is 22 out. But maybe you go in between here, put in a 7, and you get an 11 out. If you go in between here, and you input a 12, and you get a 30 out. So forget those that I just talked about. If you just collected data for this one, and this one, you're going to flip the data around. And so the X out is always 22. And then the target values are going to be 5, 10, and 15, right? So this is U. So now we're training this network. We're putting in a 22. And we get a number here, and we say, oh, the correct answer is 5. So then I put in a 22. Sorry, did I do this right? Yeah, I put in a 22, and the next training pair says, oh, the correct answer is 10. 22, oh, the correct answer is 15. If you're a student and every day I give you the same problem and I tell you that the answer is different each day, you're going to go, wait, there's a problem here, right? So that's the example of where there's not an inverse. And mathematically, to have an inverse, there has to be a one-to-one mapping. In other words, an input is mapped to a unique output, and vice versa. So if you train this, what might happen is it would learn to pick some number in between 5 and 15, and maybe it learns to give the 7, and that's not going to work, because you're going to get an 11 rather than a 22. So in math and in training here, there's a way to fix this, is you can limit the domain or restrict the domain to where you don't have duplicates. So we could fix that with this data set and just say, we're only going to use that training pair, and it would work. So one of the strategies if you're doing inverse control is you generate your training data, and then you just search through it for duplicates. You create an algorithm that looks for duplicates, and then you eliminate them. And inverse control works really well. We're going to do an example. I don't know if we'll get to it today. We might. We'll have a 2-link robot arm, and we'll do inverse control for that. That will be a project. And it works really well for a lot of cases. All right, method 3. Is neural model adaptive control. Or sometimes called impact. And one of the reasons I'm going through all of these together is that when we look at applications, like in the future, I'll come in and I'll say, okay, we're going to look at control of the distillation column. And I better tell you which one of these architectures that it uses. Otherwise, you don't know. And in fact, that's one of the things you're going to remember and learn is for which applications, what architecture was used for that. So like for an airplane flare and landing and touchdown, it's going to be copy an existing controller because it's copying a pilot. The distillation column version is what's called pseudo-inverse control. I'll show you that when we get to that. And then we do neural model adaptive control. There's a controller that was trained to back up a tractor-trailer truck. It's really hard. I can't do it. I can't back up a trailer to save my life. I go back and forth, back and forth, back and forth. Get lined up all the time. So that one is this one, the neural adaptive, model adaptive. So the way this works is we have our plant, or our system. Am I controlling the system? Probably, right? then we have our controller. And we have the issue that if we have an error here, what we wanted versus what we actually got, how do we get it back here? We can't back propagate through a box. We can back propagate through a network. So we fix that by adding a neural net model to the system. I'm putting a hat on there because what the neural net puts out here may not exactly match that. So we add a model, and what we do is we train the model to match the system. We don't even need the controller to do that. We put in a U value of 10, we get a 12.5 out here, we put the 10 into the model, and we get 5 here, and so we say, oh no, you should have got 12.5. So we train the weights of the model based on the error between these two until we get the model working really well. And then we add in the controller, and then we train the controller so we can train the model to match the system, and the error there is X out minus X hat out. And then we train the controller. I'll tell you how, but what's the error of the controller? The error is, well, what we wanted and what we got here. And the error there is X ref minus X out. And approximately it's going to be X out hat, because hopefully we train the model to do a really good job. So what do we do with that error? The error between this thing and this thing were a result of the model weights not being right. So now we have the model weights being right. So now we put in values here. What caused that error? It's got to be the controller, right? The controller did a bad job, so we're going to blame him. So we have an error here. It's this value. So what we do is we backprop through the model. We don't train the model because the model is not to blame. We backprop through the model, and that gets us an error delta. Right? Backprop gives us deltas along the way. We get an error delta at this neuron here that then we can use to train the weights inside the controller. So there's two features to this part. You train the model, and once that's done, then you backprop the error through the model to train the controller. So that's that group. A couple other methods I'm just going to give you names for, and we won't go into a lot of detail. One's called reinforcement learning, and it's kind of like intelligent trial and error. So let's list that as number 4. A more advanced version of this is genetic algorithms. I drew a blank. Genetic is spelled with a G-E, right? Yeah, G-I-N would be the drink, right? So we don't have a model in this. But what we would have on the end of this is some kind of judge or critic
that would create some kind of evaluation. Probably beyond just the tracking error, right? We've been saying, okay, the way we evaluate how good the controller does is how well this matched this, but maybe we want beyond that. We want and we want some kind of maybe energy used. So there's more of the cost than just the error. So this judge would maybe add up the cost of tracking and the cost of the energy, and then that would be how well your neural net did as far as controlling. And notice now there's no way to backprop, right? I took out the model. I guess we could put a neural net for the system and a neural net for the critic, which would work. But another way is to just pick a weight in here. So some random weight. And change it by some random value. And fundamentally change that weight, run the system all the way through, and if it made this better, we keep that weight change, and if it made it worse, we throw it away. This is essentially the trial and error. Now, a genetic algorithm is a smart way of creating populations of weights. Essentially, you're mutating the neural net. That's why it's called genetic. And this algorithm is not particular to neural nets. It's used for all kinds of stuff. But what you do is you create a population of mutations, random weight changes, and then you evaluate your system and you keep the mutations that were good and you throw away the mutations that were bad. So that's the genetic algorithm, the survival of the fittest. The downside of this is it's really slow, right? Trial and error, you know, in algorithms is slow. You just keep trying stuff. It works, you keep it. There's strategies to accelerate this. But the advantage here is that you're not limited to some simple cost functions or critics. You can make this judge anything you wanted. So you can do that. We won't look at an example of this. I just wanted you to be aware that you may see a paper in the future that that's what they do to train the network. Yeah, so advantages are you don't need a system model. You can handle all kinds of performance measures and critics. You're training the controller directly. The disadvantage are it's slow. And then the last method I'll show you. I will show you an example of this. This is method 5. It's called adaptive dynamic inverse control. I'm going to ditch this one. I found if I lay it up here, then I pick it up and I keep it, so I have to throw it away. So this kind of falls into the idea of inverse control. That's why the name's there. But let's say we have a system here. I'm actually going to give the system a name. It's a function f. So this function of the system takes a u and gives us an output. If I have some kind of math model of the system, we're going to call it f hat because it may not match exactly the system because I don't have a 100% accurate math model, but I have a pretty good math model. then if I have this math model and I can invert it, then I'm not relying on a neural net to do the control, because I say, well, I'm just going to invert that thing and use a bunch of equations to do my inverse. And if this is a perfect inverse, xref is going to go through and give me the u that then goes through the system f to give x out, right? Because the inverse simply flips this function to give me what I want. But if f hat is not a perfect inverse, it doesn't match this, because our model is not exactly matching. There's some modeling error, maybe there's some noise in the system, maybe there's wear and tear we don't know about. Then we're not going to get the perfect output here. And so what you do is you put in a neural net to add in a correction factor. And so this thing adapts and it looks at, let me get my signals right, it looks at what we got and it looks at what we wanted. And it changes itself, it changes the signal here so that you do get the exact match here. So it's going to fix up, essentially fix up the error in my models. Now, I'll go through this in more detail, and again, these are just kind of pictures that I'm drawing. There's a lot more details to how this actually works. But NASA spent a lot of time on this thing. They called it Integrated Resilient Adaptive Control, or MRAC, Modified Resilient Adaptive Control, and flew it on a couple of airplanes. And we did some work in this here and flew it on a Bonanza aircraft. And it definitely could adapt to failures, like part of the wing would fall out. We didn't have the wing off the Bonanza. But we demonstrated that if you had failures, even damage to the aircraft, this thing would adapt and allow the pilot to fly the aircraft. The advantage here is that the neural net is not doing anything as long as the model is pretty good. And so there's issues with certification when you have learning going on in an aircraft system. And the idea was we would get around that. All right, so today was the big picture. Here's the names of different control architectures. And you will be doing several of these for different assignments in the class. Right now you're doing system modeling. The next one will be the inverse control of the two-link robot arm. I might take a few minutes just to draw it and then we'll get into it next time. On the various exams, pay particular attention because I may give you a system and I'll say, show me how you would do reinforcement learning. Well, I won't do that one. Show me how you do adaptive dynamic inverse. Show me how you do the neural model reference control. And so you'll draw pictures just like I did here and explain how you do it. The system that we'll get into the details of next time is a two-link robot arm. And we will do inverse control. So here's a base for the robot. Two links that are attached to rotary joints. Yes. And the idea is to put the end effector at a certain location out in space. In other words, the robot's going to go out and grab something. And the way we control it is with these angles, give a certain angle theta 2. And so what we want to figure out is what thetas need to go into the robot to give us a target end effector location. like that. And the way we approach it with neural nets for this example, because it's an example of inverse control, is we train this by inverting the robot. Because we want to send the neural net the positions we want to be at, and the neural net's going to figure out what angles need to be put to the robot to get those positions out here. Works really well. You'll do this to track some different patterns out here. I think it's an X and an O. And this is a little more difficult because you've got to figure out what values you're going to put in here to generate the thetas that then you flip to training. I'm sorry, the other way. You're going to have to figure out what thetas you put in here to generate the X's that then you flip to training. Again, it's not difficult. It's a good example of inverse control. It's real simple and mechanically simple, but yet allows you to explore how to do that. I have to go to my office to get a link, but I want to show you one more thing. It's a cool application of neural nets that I just discovered on Tuesday. Let's see. Here we go. Yeah, so let me share this screen with you folks. So get the right thing. It doesn't look right. Well, this painting, it's obviously an impressionistic painting, was generated by the thing called a generational adversarial artificial neural net. Or generative adversarial network. What this thing does is it has a network, it's called the generator network. You can send in some noise. And you train it, in this case, they trained it to reproduce a set of images. And then on the end of this is a discriminator network that decides whether it's real or fake. These things compete. This thing competes with the discriminator to try to generate new images based on its data set that look real. And the discriminator tries to say, oh, that's a fake. versus the real. Now, I'm not going to get into the details because there's a lot behind the scenes. But they did this with a bunch of impressionistic paintings. Two French students did this in computer science. And the result, one of the images they generated was this painting here from Edmund Bellamy, I think is the name of it. And for fun, they decided to print this out, put it in a frame. They didn't tell them, they didn't say it was real. They said this was a fake painting generated by our computer program based on all these other paintings we scanned in and processed. And some people in the art world said, let's sell this at auction. They thought, well, that'd be fine, you know, maybe we'd get a couple $100 for this painting at auction in Christie's. I think Christie's is in London. Guess how much the painting sold for?
10 million.
Well, no, not that much. It's still a lot. It was like $450,000. Because people bid it up because it was this unique thing generated by this cool neural net. How it works, I may show you a couple other examples. It's being used by, there's a computer science working for me on another project to generate other aircraft maintenance data that fits the statistical distribution of the data that we already have. So it's essentially creating extra data from this maintenance database that we can use to process. It's been used to copy and create music. It's created a new musical song, a composition that doesn't sound like the stuff that was fed into it, and yet sounds like a good song. People have been trying to do that for a long time with mixed success as to, you know, what comes out doesn't really sound that much different than the stuff that was fed in and things like that. More nefarious uses, I don't know what I was trying to say. More nefariously, people are using this to create what are called deep fakes. All the way from creating fake Facebook profiles that sound real to creating images and videos of people that they want to get, you know, like politicians. They want to put out a fake ad that shows this person in a video doing something that they didn't do. So there's all kinds of nefarious stuff as well. The government's obviously interested in this because they want to be able to detect, you know, maybe passports that are fake or IDs that are fake or data that's coming in, you know, intelligence data that's fake. So both sides of this would generate fakes that might be useful. But then this end of it could detect fakes if it's really good and figure out, well, what's fake and what's real. So some of this is really cool. Some of this starts to get a little scary because you look at machines being able to do this kind of stuff, you know, and pretend to be a person as a bot on a website. And I'm sure you guys have seen the Terminator movies, right? So you couldn't look too far into the future and say, yeah, the machines may be really going to take over the world if we give them enough power. A series of books I read a long time ago, I don't know if you read them, there was an author named Isaac Asimov. You heard of him? Yeah, I think he wrote the book, the movie that Will Smith was in called iRobot. He wrote a whole series of robot books, and in those books, he established in fiction what he said were the 3 laws of robotics that were programmed into the robots to protect humans from them. And he just creates this whole web of stories around the robots and the 3 laws. I've forgotten what they are. I think one of them is they can't kill a human. Another one is they can't do anything that would harm a human. And then the third one's like they can't do anything that would harm another robot or something like that. I guess I should look it up. But these are cool, and again, if I can figure them out, we're trying to use them in another machine learning group to do quantum computing. So if anything cool comes out, I'll let you guys know and get you up to speed on this. All right, I think we'll call it good for today. You have an assignment, take time to get started on that. First thing you can do is just take those equations and generate the data. That's easy to do. You can sit down in a half an hour and do that spreadsheet right now.
I'm using guys, I forgot to switch out, the only thing I wrote on the board was 450,000.